Have you ever wondered how a robot perceives the world around it? How does an image captured by a camera, essentially a table of numbers, transform into what we understand as the world? A world where a robot can make intelligent decisions. In this video, we'll take a single photograph and explore how an engineer can design a system capable of understanding its contents. Just like most of the content on this channel, I've prepared the Colab code, which includes all the code elements I'll be demonstrating in this video. You'll have the opportunity to run these codes yourself directly from your web browser, so stay tuned for that. So, in front of us, we have a photograph. To us, as humans, it's easy to identify various objects within it: churches, pedestrians, trees, a monument, roads, and more. But to a computer, it's just a sea of numbers. Let's zoom in on this photo to see the pixels up close. Each pixel is represented by 3 numbers that define the amount of red, green, and blue in that specific spot. Today, our mission is to build a system that can decipher these numbers and understand what objects are present in this photo. In the upcoming parts of this video series, we'll delve into image classification, object detection, and image segmentation tasks. And by the end, you'll have a comprehensive understanding of how to make a machine truly see and comprehend the world through the lens of a camera. In the next part, we'll kick off with image classification. Stay tuned for that. The first step, as always, is to open the Colab document and connect to the virtual machine. Once you're set up, navigate to the first chapter in the Colab document, Image Classification, and let's run the code in it. The code you execute will run 2 models. Let's call them M1 and M2. Model M1 classifies images into almost 22,000 different classes, while M2 classifies into 1,000 classes. But what is image classification, you might ask? It's the task of describing a picture with a single concept or word. Take a look at the photo before us. Model M1 has assigned it to the class Minster, with a probability of 39%. Cathedral, with a probability of 18%, and church tower 7%. Not bad, right? What are your thoughts on this classification? Model M2, on the other hand, has assigned this photo to the class Castle with a probability of 24%. Palace, with a probability of 20%. It's a pretty good guess as well. Now, let's put the code analysis aside for the moment and jump right into the second chapter, object detection. The nature of this task becomes evident when you look at the results displayed in the photo. In this case, the model determines not just what's in the image, but also where these objects are located. The probability provided gives us an idea of how confident the model is in its answers. It's evident that the model has accurately identified 20 objects in this instance. The number of objects we intend to identify is a parameter that we can specify and pass to the model. Later in this tutorial, we will take a closer look at the code and delve into the fundamental concepts of image classification, object detection, and image segmentation. However, for now, stay tuned as we venture into the challenging world of image segmentation. Image segmentation is just the art of pixel-level classification. It is the third and most challenging task in the realm of image processing. This task involves assigning each pixel in an image to a specific object class. What makes image segmentation so captivating is its ability to provide highly precise boundaries for objects within an image. Unlike object identification, image segmentation allows us to determine object boundaries with much greater precision. In our example, the model segments the pixels into 150 different classes. As you can see, we have a collection of 150 images right here, each of them displaying the pixels that correspond to a particular class within the photo. For instance, the tree in the photo is meticulously outlined on the corresponding pixel map. From the presented images with 150 classes of pixel classification, we can see that the model was able to distinguish 7 classes: building, tree, road, grass, sidewalk, person, plant. This model is built on the HRNet v2 architecture, boasting 48 weight layers. It was trained on the ADE20K dataset, which encompasses 150 semantic categories. Therefore, it's reasonable to acknowledge that this model may not be capable of identifying all objects within the photo, given the complexity and diversity of objects in a cityscape. Now, let's visually represent these 4 classes by superimposing a pixel map onto the photo. As we can observe, the model accurately outlined the contours of the desired objects, showcasing its capabilities. Now that we've grasped the essence of these 3 image processing tasks: image classification, object detection, and image segmentation, let's dive into the code analysis. The first step in this journey is to download the relevant model from the TensorFlow Hub portal. Hub load. This line of code utilizes the TensorFlow Hub library to load a pre-trained machine learning model from a specified URL. TensorFlow Hub is a valuable resource for accessing a wide range of machine learning models and assets. It's designed to load pre-trained models, weights, and other assets from a given URL. Let me guide you through the process of discovering relevant models. Head over to the TensorFlow portal, select the image processing section, and then opt for image classification. The system will present you with a plethora of models, each distinguished by its architecture, size, and the dataset on which it was trained. For our image classification demonstration, we've picked the following configuration: architecture, EfficientNet v2, dataset, ImageNet 21K, resolution. Determining the model's size is set to 384. On the model's card, you'll find all the necessary details, including a sample Colab document to assist you. With this information, we complete the first step by downloading the image classification models M1 and M2. In a similar fashion, you can discover models tailored for object detection and image segmentation, opening up a world of possibilities for various applications and tasks within the field of machine learning and computer vision. Now that our model has been selected, the next crucial step is data selection. In the provided Colab document, you'll discover that over 90% of the code is dedicated to data preparation. In our case, this involves choosing an image and converting it into a format compatible with the downloaded model. As our data consists of a single photograph, I've taken the liberty to create interactive forms within the Colab document. These forms allow you to select an image from a list of options. Don't hesitate to customize this form to your preferences. I strongly recommend doing so. This not only facilitates a more engaging learning experience, but also highlights that image processing can be as enjoyable as playing a video game. Colab's interactive forms showcase the ability to create engaging, user-friendly applications within the Colab environment. One of these forms is specifically designed for image selection. We define a variable called ImageName, and with the help of a special comment, indicated by param, we instruct Colab to generate a user-friendly data entry form for this variable. Once you've made your image selection, we proceed to execute the Run Model on Image method. This method provides you with class names and their respective probabilities, all neatly presented in a single line of code. Additionally, the second data entry form within Colab demonstrates the process of cropping a specific section of the image. This allows you to perform classification or other tasks on the selected area. This approach is applied similarly to tasks like object identification and image segmentation. Conclusion. I hope you've noticed how straightforward it is to implement these image processing tasks with the right libraries and tools. This opens up a world of possibilities for those interested in computer vision and AI. I invite you to fully explore the provided Colab document and experiment with the code. Play around with different images, try out different models, and see the results for yourself. If you have any questions, don't hesitate to leave them in the comments under this video.